This material has been excerpted from the college television course, The Mechanical Universe, and re-edited specifically for use in the high school curriculum. The Mechanical Universe is funded by the Annenberg CPB project, made possible by a grant from the National Science Foundation.
In the beginning, there was light. Eventually, there was a light bulb. And the fact that the hotter its filament, the brighter it glows. Who would have thought that such a common phenomenon would have set the scientific imagination on fire? In fact, all glowing bodies, from a coal in a furnace, to an ember in the fire, from molten iron in a steel mill, to the filament in an incandescent light bulb, the behavior is remarkably alike. No matter what it's made of, the color with which a body glows depends only on its temperature. In fact, if they have the same temperature, all these bodies will glow with the same color. It's an amazing fact, and in Germany, Dr. Max Planck believed it deserved a good explanation. Planck's problem stemmed from applying Maxwell's theory to predict the amount of light a glowing body would radiate at each frequency. Of course, James Clerk Maxwell's theory was still the final word on light and other forms of electromagnetic radiation, and properly so. But it couldn't account for the fact that, as soon as any body becomes hot enough to glow, it glows red. Why? Why wasn't more higher frequency, bluer light radiated as well? In all glowing bodies, why should there be less light at a higher frequency? Intuition told Planck that all could be explained if it takes more energy to make light at higher frequencies. And even though there was nothing in Maxwell's theory to suggest that the energy of light may be related to its frequency, Planck wrote an equation to substantiate his intuition. The energy of light, E, is equal to a constant, h, times the frequency, f. If true, this equation would reveal a new and fundamental truth about nature. Whether by an electrical device or the sun itself, light is absorbed or radiated in discrete bundles of energy. The idea was radical and disturbing, but confirming evidence was on the way. And the evidence can still be seen today in the behavior of a gold leaf electroscope. When the electroscope is charged, the leaf rises and stays aloft until it's hit by a beam of ultraviolet light. An ordinary piece of glass transmits visible light, but it blocks the high-frequency ultraviolet light. When it's interposed, the electroscope doesn't discharge. But when the glass is removed, the leaf falls again. This proves that the ultraviolet light does the job, and it's called the photoelectric effect. It was Albert Einstein's explanation of the photoelectric effect, and not his theory of relativity, that would eventually win him the Nobel Prize in Physics. And, in modern terms, here's what he said. An electron in a metal lacks enough energy to escape by an amount called the work function. But if an electron absorbs ultraviolet light that arrives in a bundle having the energy given by Planck's formula, then the electron can gain more than enough energy to escape from the metal. If that's the case, it can come out with kinetic energy equal to h times F minus the work function. This is called Einstein's photoelectric effect equation. While each metal has a different work function, Planck's constant has the same universal value for all of them. But this explanation of the photoelectric effect not only confirmed Planck's theory, it showed directly that the bundles of energy already exist in the electromagnetic field. In other words, light comes in particles which are now called photons. But wait a minute. A century earlier, Thomas Young had proved that light travels in waves. Was it now going to turn out that light is really made of particles after all? Perhaps this whole business of particles and waves was in need of an entirely fresh perspective. Louis de Broglie got a history degree en route to a career in French government, a fresh approach to physics if there ever was one. Maybe that's why in the 1920s he was the one to ask a crucial question. If light waves can be particles, is it possible that particles, such as electrons, can also be waves? To begin with, particles have energy and momentum, while waves have frequency and wavelength. Obviously, these entities have different kinds of properties, but de Broglie suspected there was some sort of connection, and Planck's theory had given a clue to what it might be. Max Planck had associated the energy of a light particle with the frequency of its wave. Going a step further, de Broglie combined this with a particle's energy, according to Einstein's relativity theory, E equals mc squared. This bold mixture of wave and particle properties suggested the next step. Could particles, traveling at less than the speed of light, have their momentum related to their wavelengths? De Broglie believed so. He thought that just as a particle's energy is related to a frequency, a particle's momentum is related to a wavelength. It was a radical idea. Not only can light waves behave like particles, but particles can behave like waves. But within a year, experiments had verified that beams of electrons interfered and diffracted much like beams of light. And even beyond that, de Broglie's idea seemed to explain a most mysterious aspect of Niels Bohr's model of the atom. Bohr's theory was built on the notion that electrons can only exist in certain sized orbits, only in those orbits and nowhere in between. But if electrons are viewed as waves, called matter waves, circling a nucleus, they have to exist in orbits that increase a whole wavelength at a time. That way, each orbit consists of electron waves that interfere constructively and reinforce themselves on every orbit. When combined with de Broglie's formulas, This idea exactly reproduced the orbits of Bohr's model of the atom, because the angular momentum of each orbit would be an integer times h bar. On balance, Louis de Broglie's idea had been brilliant. It had given an insightful and elegant explanation of Niels Bohr's model of the atom. It had been supported by solid experimental evidence, and, not surprisingly, it drove other physicists ever deeper into the nature of matter. In Austria, Erwin Schrodinger pondered the implications of the Frenchman's work and produced a theory of his own that took off from de Broglie's ideas. Schrodinger understood that rather than being confined to an orbit, an electron matter wave could exist anywhere in three-dimensional space. His new quantum mechanics could describe not only the hydrogen atom, but all the atoms of all the elements of the natural world. And it's based on some elementary matters about waves. A wave has an amplitude and a wavelength, but no beginning or end, and nothing like the definite position of a particle. That remains true if a wave of the same wavelength is added, either in phase or out. But if waves of different wavelengths are added, the resulting shape is altered. And if those wavelengths are close together, and especially if more waves of nearby wavelength are added, the result can be a kind of wave concentrated in a limited region of space. So, with a range of wavelengths, and therefore a range of momentum, a wave-like object can be constructed in a fairly definite place. It isn't really a particle, and it isn't really a wave. What in the world is it? It is the clearest possible description of the nature of photons and electrons, of the matter which makes up the universe and everything in it. And as an idea in 1926, it was the heart and soul of Erwin Schrödinger's wave mechanics. Light passing through two slits causes an obvious wave interference, which clearly reveals itself as a pattern of light and dark stripes. There is no question about light being a wave. Only waves behave this way. So the question is, how can light be particles and still interfere like waves? If light is made of photon particles, individual little things which can't arrive as a spread out pattern, then each particle has to hit the screen individually. A single spot of light here, for example, another photon there. It's impossible to predict precisely where any spot will appear, but it is possible to see that more photons land in some places than others. In fact, there's a higher probability that more photons will land in certain regions. And eventually, because of those probabilities, the result will be a definite wave-like diffraction pattern of particles. This was the explanation proposed by Max Born. Photons might be particles, he said, but the patterns they make are ruled by probabilities that interfere as waves. And one of Born's colleagues, Werner Heisenberg, took that idea one step further. Because particles are associated with probabilities that interfere like waves, he said, it's impossible to know both the exact momentum and the exact position of any particle at the same time. The idea may be a little hard to grasp, but that was just the point. Particles, being waves as well, are a little hard to grasp. The nature of a regular wave with a definite wavelength is to spread out in space. If this wave represents a particle, then its wavelength translates into a definite momentum. However, nothing here accounts for the particle's location. The particle's place can be made more definite by adding wave after wave of different lengths. But each new wavelength means a new momentum. In other words, the more one knows about where a particle is, the less one can tell about where and how fast it's going. As the position of the wave becomes more definite, the momentum of the particle becomes less so. That relationship, delta x times delta p is approximately equal to h bar, is called the Heisenberg uncertainty principle. Werner Heisenberg, searching for deeper scientific truth, had raised uncertainty to the level of a fundamental principle of nature. According to the Heisenberg uncertainty principle, because an electron has little mass, it must occupy a relatively large region of space. Conversely, the proton has so much mass that it needs to occupy virtually no space at all. The result is the quantum mechanical hydrogen atom, a tiny, massive nucleus surrounded by a cloud representing the electron. More precisely, the cloud represents the probable position of the electron, and that probability is largest near the nucleus and decreases rapidly farther away. However, the probability of finding the electron at a given distance from the nucleus increases at first just because the volume of a shell at that distance increases. It reaches a maximum value as the shell expands, then decreases again as the electron cloud thins to almost nothing at large distances. Amazingly, the radius of the maximum is precisely equal to the radius of the first orbit of Niels Bohr's model of the hydrogen atom. Drawn to something universal in the nature of all glowing bodies, Max Planck discovered that light is radiated in little bundles of energy. When Albert Einstein solved the photoelectric problem, he confirmed that Planck's energy packets exist as particles in the electromagnetic field. Combining the insights of both Planck and Einstein, Louis de Broglie suggested that not only could waves behave like particles, but that particles could behave like waves, a wave-particle duality. Erwin Schrodinger understood that if enough waves of different lengths are added together, the result is a wave that's concentrated in one or another place, like a particle. Then Max Born saw that while it's obviously impossible for one particle to create a visible wave pattern, a cluster of particles whose behavior is determined by probabilities can fall into a pattern that looks very much like wave interference. And in that very fact, Werner Heisenberg saw the trade-off between the particle quality and the wave quality of light. When the uncertainties of position and momentum are combined, the product is approximately equal to Planck's constant. And that, beginning with Max Planck's constant and coming full circle, is the irony. Planck's quest for truth became a journey that led to the heart of quantum physics. Yet, to the end, he himself never accepted the profound implications of his own work. And for that matter, neither did Albert Einstein, who said, "It seems hard to look in God's cards, but I cannot for a moment believe that he plays dice, as the current quantum theory alleges he does." It would take new generations of bright young scientists to accept fully the astonishing implications of the new theory. They honor and obey the laws of classical mechanics, but embrace quantum theory as well. For by now, no one can deny the theoretical perfection of the new physics, nor the fact that it actually works.
This material is based upon work supported by the National Science Foundation under grant number MDR 8751537. Any opinions, findings, and conclusions or recommendations expressed in this program are those of the authors and do not necessarily reflect the views of the National Science Foundation.